is the Temple Group webinar series for 2021. This is on noise and infrastructure. How can we minimise acoustic impacts on people and the environment? Can you go to the next slide, please, Carla? So just a bit of introduction and how it's going to work out. So I'll give a bit of an introduction on the Temple Group itself. Oliver Bewes is going to talk to us about the work that he's doing with HS2, and John Fisk and Steph Murphy from the Temple Group are going to talk to us a bit about the acoustic deterrents work they've done with bat mitigation. And then at the end, what we'll do is keep the questions till the end, and then we'll have a bit of a Q&A then. Next slide, please, Carla. So just a bit of housekeeping. As I said, we'll keep all the questions until the end of the presentations. All questions can come through me. If you can either raise your hand, or possibly what might even be better is if you just pop your questions in the comments box, but then I'll come to people if you want to ask the questions yourselves, or I can read them out from there. Hopefully we can answer all of the questions, and if you can keep your mics and your videos muted and closed until question time, that would be great. Next slide, please, Colin. So just a bit of an introduction on the Temple Group. So the Temple Group is one of the UK's leading independent infrastructure and property consultancies specialising in environment, ecology, planning and sustainability. Our dedicated people deliver specialist advice to infrastructure, public sector and urban regeneration sector clients. We cover a multitude of disciplines these days, from planning, EIA infrastructure and property, ecology and arboriculture, noise and vibration, air quality and climate change, socio-economic and community, digital delivery, policy and strategy, surveys and monitoring, and construction environmental management. And our vision is putting communities and the environment at the heart of decision making. Next slide, please, Carla. So the first presentation today is from Oliver Bewes. Oliver's been working in acoustics for, I think, nearly 20 years, Oliver. His experience on major infrastructure projects includes EIA in support of DCO for new runway capacity in the UK, prediction of ground-borne noise and vibration for high-speed rail, EIA for high-speed rail, the design of track systems for cross-rail bored tunnels, the design of noise mitigation for the DLR3 car upgrade and noise and vibration services for East London Line and the Thameslink programme. Oliver is head of noise assessment at HS2 and will be telling us about HS2's civils contractors are designing phase 1 of the railway to deliver HS2's commitments to minimise noise from the railway. So over to you, Oliver.
Thank you, Nigel. If you just bear with me while I share my screen. If someone lets me know whether they can see that, that'd be.
We can see.
Fantastic. Yeah. So thank you, Nigel and Carla, for inviting me today. The title of my talk is Reducing Operational Noise as Far as Reasonably Practicable, and that sounds very much like official legal speak, and I guess that's because it is. This is you'll find out in my presentation today that that's very similar to the wording in our overarching commitments that we made when we got planning permission for the scheme. And I think the goal of my presentation today is to demonstrate how this commitment has influenced the way that we're designing the railway. My job title is Head of Noise Assessment. I work directly for the infrastructure part of the business that oversees all phases of the project, and so I split my time between working with the contractors who are currently building phase 1 of the railway, and soon to be building phase 2A, because we got royal assent last week, and also overseeing the hybrid build process for phase 2B. So my talk today, I'm here because noise and vibration from construction of HS2 could adversely impact on people. Many years ago now, we set out the local and route-wide effects of High Speed 1 in the phase 1 environmental statement and the phase 2A environmental statement, and we're currently doing that for phase 2B. And on phase 1, at the time of the hybrid bill, we committed to take all reasonable steps to reduce noise from the railway. And so now we're at a point where the railway has started construction, and so I'm trying to give you a view of how this commitment has influenced the way we work. I'm going to briefly talk about high-speed rail noise and vibration sources, a UK noise policy and how this led to HS2's noise policy, talk about how we're applying noise mitigation to the scheme, and then provide you a case study from phase 1, which is an approved Schedule 17 application for noise mitigation at West Ruislip portal. So I'm sure most of you know what HS2 is, but I know we have a few overseas attendees today. And so HS2 will be 345 miles of brand new high-speed track, which will connect Birmingham, Manchester, Leeds and London. Our trains will also run on the existing network and will serve towns in the northwest, northeast and Scotland. And it will connect 30 million people in 8 of our largest cities, with 25 stops between Scotland and the southeast. So what generates noise from a high-speed railway? Well, it's there's many different sources of noise. This kind of gives you a very general overview. We have noise from the pantograph at the top of the train. That's a particular potential issue for high speed. We have traction noise. We have aerodynamic noise from the body of the train, which is a phenomenon only associated with high speed rail. We have rolling sound from the wheels and the track, and we have ground-borne vibration from the generated when the train passes over the tracks. Other sources of noise associated with HS2 that I won't be talking about today, that's stationary systems. So those are shafts and head houses and any plant and equipment we need to operate the railway, but also construction noise and vibration as the scheme is built. So how did we end up with our commitments? Well, really, we need to go back to the noise policy statement for England in 2010. The vision of noise policy is to promote good health and a good quality of life through the effective management of noise within the government policy on sustainable development. And the noise policy has 3 key aims. That's to avoid significant adverse impacts of noise on health and quality of life, mitigate and minimise adverse impacts, and where possible, contribute to an improvement. And the noise policy statement for England introduces the concept of effect levels, which are used by the WHO in toxicology, but we can also apply those to noise. And the effect levels are the no observed effect level. So when noise is below this level, there's no detectable health on the health and quality of life due to the noise. The lowest observed effect level, and when noise reaches this level, effects on health and quality of life can start to be detected. And finally, the significant observed effect level. So above this level, we anticipate significant adverse effects on health and quality of life. And planning policy guidance noise, initially from 2014 and recently updated in 2019, provides this useful hierarchy, which tells us what the response to noise in between these effect levels can be, and the examples of how this will affect people. But I think importantly for HS2, as it sets the kind of the action that developments are expected to take when noise exceeds or is in between these certain effect levels. So this led to a very particular way of presenting our environmental noise information in the environmental statement for phase 1. This noise map presents information that's compatible with the hierarchy. The grey noise contour on the screen shows the extent of noise exposure above the LOL. The red line shows the extent of noise exposure above the SOL, and we identify properties that are between these two levels. We identify whether they're impacted with a change of noise. And we also provided noise contours in bands so that a stakeholder could understand the level of exposure in their property. So that was the environmental statement, and at hybrid bill stage we also submitted 4 key information papers which set out HS2's commitments, and each information paper refers to the key sources of noise that I've discussed: control of airborne noise, control of groundborne noise and vibration, control of noise from stationary systems, and finally our proposals for monitoring noise once the scheme is operational and the steps we'll take to rectify when noise doesn't meet our expected conditions. I've only got 10 more minutes or so, so I'll only be talking about E20 today, which is the control of airborne noise from the operational railway. And incidentally, phase 2A of the scheme had a set of almost entirely equivalent information papers, and it's the intent to submit similar papers for phase 2B as well. So I won't go through the papers in detail. I'll just go through a total of about 7 paragraphs. And so I think the key ones are the objectives of information paper E20. And so the first one is that the nominated undertaker, that's HS2, will take all reasonable steps to design and construct altered roads and to design, construct, operate and maintain the operational railway so that the combined airborne noise from these sources predicted in all reasonably foreseeable circumstances does not exceed the lowest observed adverse effect level. And that's the second aim of noise policy statement for England. Where it's not reasonably practicable to achieve this, we'll reduce airborne noise from altered roads as far as reasonably practicable. That's also in line with the second aim of the noise policy statement for England. And we'll offer noise insulation with the aim, we'll offer noise insulation when noise exposure is above the SOL. And so that's the first aim of noise policy, to avoid significant adverse effects. And where possible, we'll contribute to improvements in health and quality of life. So that's the third aim of noise policy. And secondly, we have the control measures that we've committed to take. So we've committed to reduce noise generation at source. So that refers to the specification and design of the train and the track. To reduce noise propagation through the design, specification, construction and maintenance of noise fence barriers and or landscape earthworks. So that's referring to the civil engineering, which I'm mainly talking about today. And finally, to reduce the amount of noise entering eligible properties through the offer of noise insulation. And and to ensure that the measures control airborne, that the measures that control airborne noise are reasonable, we need to take account of the set of shared UK principles that underpin the government sustainability strategy. So that's really saying there has to be a sustainability test for mitigation. Most of the time we can always reduce noise further, but we need a way of demonstrating that the amount of noise mitigation we're providing is reasonable and doesn't cause other impacts or engineering issues or visual impacts, but I'll come back to that. So in terms of responsibility, in our control measures, the noise sources relating to the train and the track are to do with the rolling stock and our rail systems, and those are subject of design and specification, possibly the subject of another talk. And the noise mitigation is the responsibility of the civils contractors who are designing and building the railway. So the hybrid build design for phase 1 included more than 60 kilometres of noise barriers, in addition to earthworks to reduce noise. And currently our civils contractors are optimising that design in line with the commitments that I've described. So I'll give you a sort of a very indicative timeline for how we're implementing our commitments. And we're about here at the moment. I should have moved the red star slightly to the right. Phase 1 construction has commenced, and I guess so. The key milestones are the design and construction of the civil engineering works. I think the key point is we're yet to procure the track, and we're yet to procure the trains. So we're still making assumptions about how noisy the trains and tracks are going to be. And then at some point the civil works will be complete and we can install the railway systems such as the track. And then into the future we need to monitor and maintain the performance that we're predicting. Key to today's presentation are some planning milestones, and we refer to that as Schedule 17 of the High Speed 1 Act. And we're currently in this stage here, which I'll talk more about in a second, and we're at the Schedule 17 paragraph 3 approval stage for indicative mitigation. And later on, we have another approval stage called bringing into use. So I think now good time to move on to a case study. What do we actually mean by a Schedule 17.3 application? Well, the HS2 Act for Phase 1 granted us deemed planning permission for Phase 1 of the railway under Part 3 of the Town and Country Planning Act, but some detailed design and construction aspects are subject to further approvals. And Schedule 17 of the Act puts in place a process for the approval of certain matters relating to the design and construction of the railway with the relevant local planning authorities. It's not a planning application because we already have deemed planning permission, but that's it. In practical terms, it's treated like that. So Schedule 17 sets out a number of items subject to approvals, and that's plans and specifications, and which are relevant to us. And paragraph 3 talks about indicative mitigation. So that's not just noise mitigation, that can be ecological mitigation and other types of mitigation. And again, we need to provide information at bringing into use. And through the best practice that we've set up through the planning memorandum, which forms part of our commitments, we're committed to providing information on noise at these 2 stages during the Schedule 17 process. And we're required to show that we are reducing noise as far as reasonably practicable at these stages. So it's actually quite a key stage for us at the moment. Our stakeholders are very interested to know how we're performing. It's been many years now since we've provided updated noise predictions to those presented in the environmental statements. So we're being watched very closely now, and so it's quite an exciting time. We've had the application I want to talk to you about is actually the first approved Schedule 17 application, which includes noise mitigation. So it refers to West Ruislip portal, which is actually hopefully familiar from the first noise map that I showed you. But for the purposes of Schedule 17, the railway is divided into multiple assets, and a Schedule 17 application is made on an asset by asset basis or for a group of assets. And so West Ruislip portal included embankment works, a porous portal on the entrance to the London tunnels, a head house and a substation. But I think most important for today's presentation, it included an application for noise barriers. So where were we at the end of the hybrid bill? So this picture here just shows you an extract from the one of the additional provision environmental statements. So in West Ruislip, we had predicted that 156 dwellings would exceed the lowest observed effect level, and we predicted minor and moderate noise impacts. This is an increase in noise compared to the existing noise level at approximately 70 dwellings. And because of this, we'd identified a significant community effect in the community just to the south of the railway. And so the environmental statement included a 3-metre noise barrier to the north of the trace and a 5-metre noise barrier to the south of the trace. And the noise impacts I'm describing there were the residual impacts after the provision of that mitigation. So in Schedule 17 design, our main work civils contractors have the opportunity to optimise. So they're using noise prediction to test the performance of their designs, and during their Schedule 17 application, they're aiming to demonstrate that the design reduces noise as far as reasonably practicable, using both acoustics and non-acoustic factors. And these were all the parameters that were agreed with the planning forum subgroup, which is has representatives from local authorities across the route. And so these factors are the acoustic performance of the railway, so how much noise is being made, value for money. So this is the comparison of the health and environmental benefits of the noise reduction with the whole life cost of the mitigation. So as you'll see in a second, the government has tools for monetising noise impact, and we need to compare the cost of the mitigation to the reduction in noise impact that mitigation provides. So operational or engineering practicability. Is it safe to build a tall barrier on top of a tall embankment? Because we can always provide more mitigation, but there'll come a point where it's no longer practicable to do so. Impacts on other environmental disciplines. The key one is the visual impact of a tall noise barrier. We can build taller noise barriers, but do we start to create new visual and landscape impacts that weren't originally envisaged in the environmental statement? And finally, stakeholder engagement. For example, a planning authority or another stakeholder may have a preference for an earth bund rather than a noise barrier. So this slide here just shows a summary of the optioneering that went into the Schedule 17 application. And in this case, the contractor assessed 12 different noise barrier designs and compared the acoustic performance, the visual impact, the value for money, and the engineering practicability, and they came up with their preferred design. So a number of things were tested. This site didn't lend itself to earthworks because it was quite a narrow rail corridor. Earthworks would have needed more land. So generally this site focused just on noise barriers, but they tested different heights, moving barriers close to the railway, further from the railway, and cranking noise barriers, which I'll talk about in a second. And just a little bit on value for money. How do we determine if noise mitigation is value for money? Well, we use the government's transport analysis guidance tool, often referred to as WebTag, and this this provides us a means of monetizing the impact of noise based on the most up-to-date dose response relationships for the different outcomes or health impacts of noise. And so really for every noise mitigation measure, we can come up with a cost benefit ratio which compares the monetized impact of the noise without mitigation with the impact with mitigation, and divided by the whole life cost of the mitigation. So a cost benefit ratio of 1 tells us that the inclusion of that mitigation is exactly offsetting the health disbenefits created by the noise. So at this design, the contractor came up with what they termed a cranked noise barrier design. So this actually helps to improve the acoustic performance of the noise barrier because it moves the top of the barrier close to the railway, and also visual impact was a key concern in this area because this barrier could be seen. So the crank of the barrier helps soften the visual appearance of the barrier. And just a plan showing the one of the plan drawings and some more sections that are included in the Schedule 17 application. And finally, noise information that we provide with each Schedule 17 application. The noise report that we provide does give more detailed noise predictions, but also gives a summary of the overall performance. And so it was concluded that this design actually represented a material improvement compared to the hybrid bill, because if we look at the number of properties exposed to the lowest observed adverse effect level for the proposed design and the environmental statement, we can see both during the day and night the numbers have reduced compared to the design. And in terms of the impact, so this is the change in noise, we've also reduced the noise change in the communities in the vicinity of the railway. And if we were to go and assess the area again using the environmental assessment methodologies, we would say this is a material improvement in the situation that was presented at hybrid bill. So this is good news. So that's it about the design. Just one last slide on what's the next steps. Well, as I said, we've only had 1 or 2 Schedule 17 applications submitted and approved. So we're continuing to design the railway and optimize the design to reduce noise. We still need to confirm the performance of the rolling stock and specify, procure and install the track to minimize noise. And eventually we need to implement our strategy for monitoring the acoustic performance of the railway. And the picture there just shows you some measurements we made of a Volaro train in Spain in 2018 at speeds of about 350 kilometers per hour. So some of the work we're doing to assure the assumptions that we made in the environmental statement. So that's it. Thank you very much.
Thanks, Oliver. While Carla gets the slides back up for the next presentation, which is by Stephanie Murphy and John Fisk. So Steph has been working in ecology for 18 years and has a PhD in bat acoustics. She's been involved on HS2 for 9 years on the design, coordination and survey to inform the hybrid bill, and is the lead technical advisor for the Burnwood monitoring programme and the Natural England named ecologist for the Burnwood bat licence. Steph is experienced in ecological impact assessment for linear infrastructure, specifically road and rail, and experienced in designing mitigation and compensation for protected species with a specialism in Annex 2 bat species. John has been working in acoustics for around 14 years and has been involved on route appraisal, optioneering, EIA and public consultation for HS2 for the last 10 years. He's experienced in environmental impact and noise modelling and assessment of road and rail traffic noise mechanical plant noise sources, construction noise, and other industrial noise sources. Steph and John are Executive Director and Associate Director, respectively, at the Temple Group, and will be telling us about the innovative work on how acoustic deterrents can be used to deter bats from infrastructure while ensuring normal levels of bat behaviour in the vicinity remain the same. Over to you and Steph and John.
Thanks, Nigel. Carla, do you mind bring the first slide up, please? Thank you very much. So today we're just going to cover an introduction to the issue. So Oliver very much discussed how we reduce the noise impacts on human receptors, but this is actually a way of looking at how that acoustics can actually enhance bat mitigation. So we're going to cover what is an acoustic deterrent, and John will cover that, and then John will also cover the field testing, deterrent, propagation and directivity. So I'm going to provide the introduction to the issue and the requirement for bat mitigation. Next slide, please, Carla. So the trains through HS2, they're going through at speeds of 360 kilometers per hour, and this creates a potential issue for collision of bats and other species if they cross the rail corridor at unsafe crossing areas. So there's a risk of bat mortality, and if we don't, bats, unlike other species, are more mobile animals, so they can fly over noise barriers and potentially drop into the rail corridor. So how can we ensure that safe crossing points are provided for bats? So the route, HS2 phase 1 route, it passes through the Burnwood Forest in Buckinghamshire, and this is an area of national importance for Bechstein's bats. This is one of the rarest UK bat species. So all bat species are protected, but certain bat species, like woodland bat species specialists in particular, so brown lunged and Bechstein's bats, which use prey-generated noises to detect their prey, they're quite sensitive species. So the impacts of the scheme in particular include roost loss, fragmentation of habitats, and collision. So a licence has been obtained from Natural England, which sets out a very extensive mitigation package along this 8-kilometre section of rail corridor, and this includes 25 hectares of woodland planting, 5 30-metre wide green bridges, 4-metre high underpasses. There's a total of 3 of those, and a mitigation structure sorry, I think it's gone back the other way. Thank you. And a mitigation structure to prevent collision risk around a very particular sensitive area known as the Sheephouse Wood mitigation structure. So if we just go to the next slide, please, Carla. So this gives you a scale of the type of mitigation here. So here, this shows you some of the green bridges. So the bridge right in the centre of the screen, which kind of almost looks like an S-shaped bridge. This is quite an important bridge. So this is the main connectivity hub for Bechstein's bats that centres right in the middle of the licensable area. So all the woodlands in the surrounding area contains bat colonies that are very sensitive, and the bats essentially traverse the rail corridor to get to these roosting sites. They roost in trees, woodland specialists, and there's concern if they are not able to maintain that connectivity, being able to cross the rail corridor, they'll become isolated, their populations will become fragmented, and they'll end up in decline. They're at the most northwestern distribution of the European range. So if we affect the favourable conservation status of this species, it has got a significant impact at both national and international level. So it's very important that the mitigation that is put in place is effective, because the mitigation it has to be on the right location and connect to prevent fragmentation of habitat. So essentially this will allow bats to continue to cross the rail corridor. You can see the white train line which goes through the centre of the picture, and the green bridges over the top and the underpasses underneath the rail corridor allow permeability for bats to continue to pass. However, there are still a number of risk points where bats can continue to fly under the parapets, or they can fly along the portals. If you go to the next slide, please, Carla. Now, a particular challenging area within the Burnwood licence was the Sheep House wood area. So there's the Sheep House wood. It's essentially adjacent to the FCC landfill. And this is the sketch of it looking east. So there's a big triple SI woodland, which has got Beckstein's colonies. And our baseline data showed that bats were exiting the woodland to access habitats to the west of the rail corridor. So, and the proposal for the restoration of the left FCC landfill was that to replant this woodland up over time. So essentially you will have a big ancient woodland and in 50, 100 years a new woodland adjacent to that. So we would like to think that bats will continue to want to access the land to the west, but if it's bisected by trains running at 360 kilometres an hour, it presents a significant collision risk. The area is very complex, so it's an ancient woodland, a site of special scientific interest. It's an active landfill, and the network rail tracks, the challenges are very complex. So in order to prevent collision risk, a bespoke 850-metre bat mitigation structure alongside Sheep House wood is being proposed to protect bats from being struck by passing trains. But there was still an outstanding concern that at each of the entrance to the tunnel portals, at the base of the structure, so at the bottom, which indicates where bats could enter the structure or exit the structure, they're still at a risk of collision. So one of the mechanisms we looked at, well, how could we deter bats getting into the structure? How can we enhance existing green bridges to increase the likelihood of success of all of this mitigation that is being produced and constructed? Well, one of the methods we looked at originally was lighting, and that was discounted because it's not effective. And there's also the risk you can't have lighting on in this area of it's a key environmental work site, and it's also dark skies, and also there's a risk with trains. But one of the areas that we looked at in particular was the use of acoustics and how we can use ultrasound and the acoustic ultrasound to deter bats from crossing the railway at unsafe crossing points. So I'm going to go to the next slide, please. So I'm going to pass over now to John Fisk, who will discuss in detail what is an acoustic deterrent, and then we'll pass on to continue on to discuss the propagation and directivity of the deterrents. Thank you.
Hi there. Good morning. Thanks, Steph. So yeah, what is an acoustic deterrent? So I can hear an echo. Thanks. Yeah, so bats produce high frequency vocal signals, perceive their surroundings by listening to echoes reflected from targets in their path. I'm sure lots of people are aware of their use of echolocation, things like this. So they rely on that heavily for orientation, prey capture, communication, and obstacle avoidance. So the acoustic deterrent is, as Steph said, is so it's basically an array of transducers or speakers that generate noise over the frequency range of it says 10 kilohertz to 100 kilohertz, but basically in the ultrasound frequency range. For those that don't know, so ultrasound frequency range is basically anything higher frequency than a person might be able to hear. So anything higher than about 20 kilohertz or so. So yeah, basically the acoustic deterrent emits the noise. This is the noise that bats use to do all these things, to communicate, orientate themselves. And so effectively the idea is that the noise from the deterrent repels bats through communication, jamming, disorientation, etc., things like that. So I think the idea of this has come from previous work on acoustic deterrents being used as a method to avoid bat fatalities at wind turbines, particularly in the US, I think. But it's as I understand, it's not a particularly well used method in the UK. So it's there was effectively this need to do some research into the how effective it is, and look at the properties of deterrence and ultrasound propagation and things like that. So as Steph mentioned, the proposals to effectively locate the deterrents near the portals of the mitigation structure to repel the bats and stop them flying in, basically. Next slide, please. Thank you. So there's field tests undertaken. There's basically two main purposes, or two strands of the field tests. I'm going to talk about one of them. So the first one, which I won't talk about, which Steph will know more about, is effectively the looking at how effective the deterrent is at its main purpose, deterring bats. But what we also looked at is the properties of the deterrent in terms of how it emits the ultrasound and how that propagates over distance and directionally as well. And the main reason for this is effectively as it says there. So the effectiveness of the ultrasound deterrent is going to be limited by the distance and area the ultrasound can be broadcast into, and effectively things like high humidity, potentially temperature and things like this can affect quite strongly how these very high frequency sounds are actually emitted. So effectively, if the ultrasound is effectively not emitted particularly strongly, or can't be heard by the bats until they're very close to the unit, then it may affect the effectiveness of the deterrent in general. And it may also mean that you may need an array of units or a different setup and things like that. So to actually deter across a full area of a portal and things. So the measurements we were involved in is to test propagation and directivity of the ultrasound. These were done at the same time as looking at the effectiveness of the deterrent as well. We tested the device on the right, which is a particular deterrent manufactured by Deterrents with 16 transducers, and that was the one we tested. Yeah, as I say, that's what we tested. Some details on the next slide. Get to the next slide. So this is just so an image on the right of how we set things up. So the site we used was a disused railway corridor, selected due to for a number of reasons. I think a lot of reasons to do with it having plenty of bats in the area and being a similar sort of site to the Sheep House Wood area. And yeah, so measurements. So we undertook measurements with a sound level meter. It was a slightly specialized sound level meter, I guess, not your standard one, with capability of measurements up to around 80 kilohertz. Although when it gets to close to that high frequency, the background noise is a little bit, yeah, makes some of those measurements, particularly high frequencies, a bit difficult. But yeah, measurements were made at various distances with the unit. So 1 meter, 5 meters, 10 meters, 25, 50, 75, and 100. And also we orientated the unit at different angles as well to try and look at how the directivity, but how the noise, the ultrasound spreads side to side from the unit, basically. And it's a symmetrical thing, so it's expected that the directivity up and down would be the same as it would be side to side, basically. So so yeah, the experiments carried out under a special license from English Nature. And similar measurements. We also repeated some measurements in a sort of indoor location with different, effectively different humidity conditions, because just close up to sort of understand some of the really close up propagation of the unit, and in different conditions. So on to the next slide, we've got some sort of results of that testing. Basically shows that so yeah, as expected, there's the propagation of ultrasound is prevented quite significantly at long distances. So anything more than about 25. So basically, yeah, if I just explain the graphs on the right a little bit quickly for you. So because I can see they're quite small, so you might find it difficult. So the x-axis is the frequency, and that goes from basically your ultrasound frequency range, 20 kilohertz up to about 80 kilohertz. And then the y-axis is the sound pressure level. And so the different lines represent different distances from the unit. So the blue line is 1 meter from the unit, and then the orange, grey and yellow lines are 5 meter, 10 meter and 25 meters. And the other lines are further away, but effectively we weren't measuring anything at that distance particularly. Yeah, so as terms of some conclusions on the outdoor stuff, so the sound levels above 40 dB across the full frequency range within about 5 meters of the unit. So and then substantial attenuation of frequencies above about 40 kilohertz at about 25 meters. And yeah, as I say, below noise floor, so effectively we weren't measuring anything greater than 25, I would say, probably rather than greater than 50, but from 50 upwards in terms of where we did the measurement. And then the internal ones on the right, these were all done at much closer distances. So it's the same thing on the graph, but the distances are 1, 2, 3, 4, and 5 meters instead. The ultrasound actually varies quite a bit over time, so hence why they're quite similar. But it just showed that, you know, in different conditions, the higher frequencies can propagate better, and effectively it's much higher relative humidity on the outdoor measurements. So should we go to the next slide, please? And yeah, this was just, as I say, looking at the directivity of the deterrents. And so the graph on the right is basically just looking at the angle of the of instance of the unit. So Effectively, the front of the unit, the 0 degrees, is at the top. And then as you go around, so we did measurements at 10 degrees, 20, 30, 45, and etc. And yeah, so as I say, a highly directional reduction of about 10 to 15 dBs at the 10 degree angle. So so that, yeah, quite significant directionality there. And as I say, similar results shown in the internal and outdoor measurements, but obviously the internal ones are a little bit easier to measure because we were because as I showed before, we got higher sound levels from the unit at distance. So I have this was sort of the last slide I've got in terms of the results. I mean, basically, the work is still in progress on this, so we're just sharing some of the stuff that we've done so far. The Steph may also be, if people are interested, maybe also be able to talk about some of the way of how effective the deterrent was in the field trials, but basically the information I think we've gathered is useful for understanding, things like how many units we might need to use to get coverage, basically, and also to understand, look at the effectiveness of the unit and how much it was deterring bats and at what distance, and then compare that to what sort of sound propagation characteristics there were at the time. So I think that's my last slide. So you can carry it and go to the next slide. Thank you for that. Hand over to Nigel. Yes.
Thanks, Steph and John. Got a little bit of time for questions. Got a couple of questions that have come up in the chat. First one was from Martin Chan. Is this ultrasonic deterrent device to be turned on at all times? So that's one for you, Steph or John.
Well, they'd only need to be turned on at night time and during the active bat season, and at times when it's critical. So that time over the year changes throughout the season. So in the peak of the summer months in June, it'd be from 9 at night till 4 or 5 in the morning. But then and at other times in the year it would need to go on longer, October, November. And bats are very temperature dependent on their activity. So in the cold weather we've had over the last few weeks, they wouldn't be moving around significantly. So the chances of collision risk is significantly reduced. But as the temperatures start to warm up and bats start to move around and leave their hibernation sites and start to use their breeding sites, the deterrents, if there's a collision risk on an area that we know is frequently used by bats, they'd have to be on at night in those areas. But the sound the audible sound that we as humans hear it is quite contained. I mean, it's almost like a whooshing noise, but it's not. It does dissipate fairly quickly at the level we can hear it at.
Thanks, Steph. One from Telly Chanelis. How are the devices powered, and what about protection from theft and vandalism?
Good question. So in the trials, they were powered by a generator, but we're looking at going to the next step in design and looking at if they can be used on other areas of HS2, not just on in this one specific area, and we're going back to the manufacturers and asking if they can be integrated into noise barriers, if they can be powered by solar panels potentially. So the task now is to go back to the manufacturers of these devices to see if they can make them bespoke for actual purpose to use in conjunction with the rail infrastructure.
Thanks, Steph. Are any other questions from anybody? You can either raise your hand or put the questions in the chat. If not, we may as well leave it there. So, oh, John's got a question. Go on, John.
Hello. I did have a question. I had a question on Oliver's presentation, actually. If you don't mind, it's just it's really interesting presentation. So thanks for that. It's really good. And I'm just interested in you showed the reduction in impact at the West Ruislip portal. I'm just wondering whether the reduction in impact was entirely a result of the barrier, or whether other factors contributed to that.
It was a bit of a. I think it was largely the barriers, but there had been some modifications to the portal, and there's our environmental at the time of the hybrid bill environmental statement. We had made the assumption that we would have some just TSI compliant trains operating on the scheme, and that was because at the time there was the high speed 1 link, so HS2 was directly linked to high speed 1, but that's no longer planned. So for this stage of design, we've removed the noisier trains from from our assumptions, because we wouldn't have had control over the noise specification of those trains, and that's made a small improvement, but it's largely due to the improved noise barrier design.
Thanks.
Thanks, Oliver. I actually had one for you, Oliver, which was around about the assumptions on trains and tracks. Is that based on existing trains and tracks, I assume? And is there any evolution in noise reduction from new technologies or anything?
Well, we at the time of the well, sort of related to the last question. Currently, the noise level from trains, any train that travels or manufactured in Europe, is the noise levels are mandated by the TSI specification, and that still applies to the UK despite Brexit. So, but at the time of the environmental statement, we weren't actually able to mandate quieter trains, but we're able to incentivize a noise reduction. So, and there's lots of evidence out there that existing trains that haven't had a huge effort put into the noise mitigation are less than the TSI. So, in the environmental statement, we made a number of assumptions based on the research available at the time about how much quieter than the TSI HS2's trains would be, and now that's and so we've incentivized that performance in the rolling stock contracts, which are still underway. So we should find out about that in due course, and the track as well. That was all based on existing research available at the time. We've recently done, well, 2018. We completed a bit of research with the Institute of Sound and Vibration Research, looking at whether slab track would be noisier than ballast track, because that was a sort of historic assumption, and because now we know that all of phase 1 will be slab track, and we were able to show that because of the low roughness levels we expect on high speed rail and the type of rail fastening system, that slab track won't actually be significantly noisier than ballast track. So So yes, some of the information was still were assumptions made in the environmental statement, but we've done quite a bit of work since to confirm those assumptions.
Thanks, Oliver. We're just around about on time, so I think we'll close the session there. So thanks everybody for attending, and thanks Oliver and Steph and John for your very informative presentations. Thanks everyone.
Thank you.
Thank you.
Thanks. Thank you.